Thanks so much for the invitation. And so I am very excited to present this work, which was done with Justin Cady, who is definitely both a discrete and integral part of this project. And this is a store near where I live, which partly inspired the project in addition to some physics questions. Which is, if you have any orders for modular forms, you just let me know. It's right by the coffee shop I go to sometimes, and I see from this map, it's also near Walt Disney's grave, if you're into that sort of thing. So when we can all travel again, you can come to Los Angeles and check these things out for yourself. Good. So this work was driven by a few different questions which center around the main theme. So the first question is, what are the abstract implications of discreteness and integrality for the space of compact CFTs? The second is there a non-universality in ADS3 quantum black hole entropy? And the third is, what is the space of non-holomorphic cusp forms of SL2Z, that one being more of a mathematical question. And these all center around the physics question, are irrational CFTs really as wild as we think they are? So I think it's fair to say that the mainstream point of view that exists right now is fairly represented by this passage from Sheehan's 2016, I think, Tazi notes. So perhaps you started to read it already. I won't read it out loud. It's maybe worth highlighting this sentence here, that there's not a single example of a unitary compact CFT that's known to admit no extra higher spin conserved currents beyond Virasoro symmetry. And so I think, largely due to work of the past 5 years or so, gone are dated misconceptions that 2D CFT has been solved. But as this passage shows, we'd like to do better in understanding what the next steps should be to solve it. And so you could ask, what are we missing? Now, there are some things we don't know that we're missing, obviously, but there are some things that we haven't incorporated, and this talks about two of those. So the partition function of a compact CFT admits the following form. There's the vacuum module, and there's a sum over other non-vacuum modules of, say, the Virasoro algebra. In every CFT, the partition function must be modular invariant. And in a unitary compact CFT, which is typically what we're interested in, the degeneracies must obey the following three properties. The first is positivity, which is essentially unitarity, which is the statement that these degeneracies D, labeled by a left and right moving conformal weight, H and H bar, must be non-negative. The second I'll call discreteness, which is the statement that these degeneracies are numbers. They, in particular, don't depend on the complex structure modulus of the torus. And finally, there's the integrality constraint, which is that the degeneracies are integers, and we're counting something. So while much has been extracted from constraints of modularity and positivity, the same is definitely not true of discreteness and integrality. In the usual approach to the conformal or modular bootstrap, discreteness and integrality are not imposed, so they're not inputs to the computations. They sometimes emerge as outputs, for example, via optimal solutions to crossing found numerically. This is a fun quote from a paper by these authors, where they are solving crossing in a certain situation and finding, as you are probably familiar with, the J function numerically. So that's kind of fun, kind of cute, but you'd like to find a way to impose integrality from the beginning and ask what that does for you. Likewise, the existence of a normalizable vacuum is often imposed, but the discreteness of the rest of the spectrum, much less the integrality of the coefficients, which is of course a finer constraint, is not. And so the question that I posed earlier is, what are the abstract implications of discreteness and integrality, the space and properties of compact CFTs? And sorry, before I go any further, I should say, if there are any questions at any point, please feel free to ask. What we'll see is that actually, at least in certain settings, discreteness and integrality alone without positivity are enough to derive some new results of the following types. So we'll have some Bootstrap type bounds on dimensions, twists, and OP coefficients of local operators. Just as a matter of notation, I'll use delta and j for the dimension and spin of local operators, and little t as the twist, which is twice the minimum of the left and right moving conformal weight. So this is the same definition that applies in d dimensions. And we'll find some special bounds, in particular for rational points on conformal manifolds. Why those will rely on some sort of quirky property, which I'll explain later, of conformal blocks on the torus. The second will be to find some non-holomorphic avatars of features of holomorphic CFT, which is, of course, well understood. And finally, we'll understand some quantum aspects of ADS3 black holes and suggestions for holography. So let me give a slightly more extended introduction before getting into some details. So in holomorphic CFT, the spectrum of operators with dimensions h greater than c over 24 is completely determined by its complement. This is well known. It's a statement about meromorphic modular forms of SL2Z, and I'm going to call this spectral determinacy. So given the spectrum of operators below and up to c over 24, the spectrum above is completely determined. This part of the spectrum might be called the polar part of the spectrum because the contributions to the partition function diverge at the cusp at infinity. And holographically, these are like dual tube particles in ADS3. And likewise for the nonpolar and black hole part of the spectrum over here. Conventional wisdom is that in non-holomorphic CFT, this does not hold, either for the twist spectrum T or the dimension spectrum delta. And so often the logic is just that, well, we don't know so much about that space, and we don't know much about the space of those mathematical objects, non-holomorphic modular functions, so why should that be true? And it turns out that conventional wisdom in certain settings is wrong. So, for example, we'll prove that rational CFTs do obey spectral determinacy in their twist T, which is to say, all of these degeneracies are fixed by all of these. If you want to address questions like this, mathematically, what one is doing is to understand non-holomorphic modular forms. And there's relative absence of knowledge about those, well, because they're non-holomorphic. And the project actually began as an attempt to understand what was known about the space of non-holomorphic modular forms, especially those known as cusp forms, and which obey discreteness. A cusp form is one that vanishes at I infinity. And so we surveyed the literature, and actually this is how we found our first quote unquote result. There aren't any. And this is true even without imposing integrality or positivity. Now, we're going to construct some which have two of the three properties, integrality and discreteness, but not positivity, and we're going to prove that, in fact, having all three is not possible. So the mathematical question that mimics the physical question I posed earlier is this one here. And so we're going to make some modest contributions to the mathematical side of this. The physics will follow from these two mathematical results, which will prove pretty simply. So first, let me just state main theorem number one. Consider any weakly holomorphic SL2Z invariant function, f, that admits a Fourier decomposition into vector-valued modular forms of dimension d greater than 1 with a Fourier expansion like this. Now, we'll talk about vector-valued modular forms soon. These are essentially relevant for rational CFT, but not irrational CFT. If you impose integrality of these coefficients, then the leading power in the Q expansion must be negative. So that's the first result. The second result is that there do not exist non-holomorphic cusp forms, namely those that vanish as Q goes to 0 and Q bar goes to 0, that satisfy all three of positivity, discreteness, and integrality. On the other hand, there do exist such forms if you just impose discreteness and integrality alone, and we'll construct some, which, to my knowledge, are the first such explicit ones in the literature. Okay, so final slide before sort of moving on. Why cusp forms? Well, from the ADS3 CFT2 point of view, a cusp form, which has modular weight 0, represents a possible correction to the degeneracies of heavy states in a CFT. These are dual to black holes, and so these are ambiguities or non-universalities in the microcanonical BTZ entropy. If you can add a function which just changes the number of states up here, but not down here, this is a non-universal contribution to the entropy. Now, it's not totally clear that these should be allowed in a sensible theory. For example, our bias from classical physics is that, due to things like the no-hair theorem and the fact that black holes form from collapse, given some set of light particles and some profile, that you get some final state with some fixed entropy. But whether this is true at the quantum level is not clear, and we'll argue that absent certain types of fine-tuning, these ambiguities are not allowed. And in CFT language, the statement is that typical irrational CFTs, where by typical, I'll explain what I mean later, do obey spectral determinacy after all. Okay, so the plan for the rest of the talk is as follows. First, I'll just briefly introduce some of the concepts a little bit more cleanly. Then we'll talk about the twist spectrum of CFTs, and this will involve studying vector valued modular forms and put us in the realm of rational CFT, because that's where we can do a lot of damage. Then we'll back up and go back to the general questions about non-holomorphic forms, and we'll make some statements about the dimension spectrum of CFTs, irrational CFTs. And finally, I'll make some comments about 3D gravity in both ensemble and non-ensemble interpretations. Okay.
Eric, I have a question. Maybe you already mentioned this, or maybe you are going to discuss it further, but I'm a little bit confused about whether there's a sharp distinction between a CFT with discrete spectrum versus a non-compact CFT. Because I can imagine we have a lot of examples of, say, sigma model CFT, where I can take the volume of the target space to be very large in a continuous fashion. And then this limit will, then I will have a series of compact CFT approaching a non-compact limit. So I'm a little bit confused how to draw a sharp line separating these two cases.
I think what's important is that we're insisting on there being a normalizable vacuum.
Okay. Okay, that makes sense. Okay, okay, thanks.
Sure. Any other questions?
Eric?
Yes.
Can I ask you a little more? I think you mentioned it earlier, but how do you define non-holomorphic cusp form in the following sense? If I take tau to I infinity, but keep tau bar fixed, do you demand that it vanishes then or not? To be a cusp form?
Let's see. Do we actually demand that? That is not a cusp form for us. No.
Okay. I think, thank you.
Yeah. Mm-hmm. Okay, and I think it'll be clear later why that would make a difference. Okay. Good. So just some definitions first. So we're going to call our functions f. A function which has weights w comma w bar under SL2Z transformations, well, it transforms like this. And we're going to deal almost entirely with weight 0, comma 0 functions, forms, aka modular functions. And we're going to take them to have Fourier expansion like so, with q and q bar defined in terms of tau and tau bar, which in turn are defined in terms of tau 1 and tau 2, like this. Discrete, by the definitions I gave earlier, means that these, which can be functions of tau 2 in general and still be consistent with t invariance and s invariance, we're taking them to be constant. Integral means that they are not just constant, but that they're integers. And we are often going to restrict to the diagonal, by which I mean q bar equals q, in which case the expansion takes the following form. We have these powers of q and then some more powers of q, and the leading power is denoted here as m naught plus m naught bar plus x tilde. And if we define x naught as the sum of those three, then the form is cuspidal if x naught is positive. So this should actually be positive, not greater than or equal to. So that means that when you take q to 0, the form vanishes. A CFT partition function has weight 0, comma 0, of course. Sometimes one is interested in counting primaries by appending 2 powers of the eta function, and then this object ZP has weight a half comma a half, we will almost exclusively just use the weight 0 guy, but this is just worth mentioning for contact with the literature. And we'll use this one time later. So with some of this notation in place, the following 2 CFT questions about spectral determinacy in twist T and dimension delta, namely do they, the spectra at or below C/12 uniquely specify the spectra above, can be translated or related to the following 2 mathematical questions. First, do there exist modular functions with integral Fourier coefficients and positive values of m0 and m0 bar? This is the question of twist, because m0 and m0 bar are the powers of q and q bar separately, and twist is a statement about h or h bar separately. And the second question about the dimension spectrum gets related to the question, do there exist cuspidal functions with integral Fourier coefficients and x0 positive? Right. If there did, then the answer to this question here would be no. As we'll see later, it's a little more subtle than that, but that's the relation. And the answers will depend crucially on whether we impose discreteness and integrality as demanded here. So let me actually skip this, just in the interest of keeping people's attention. It's up here. You can look at it further later. But instead, we're going to just proceed right to the first question about twist spectra, and we're going to answer this in the realm of rational CFT. Okay, so VVMF stands for vector valued modular form, which I should have written somewhere. If you have a modular function f, and we write it as a sum of some gluing matrix Nij times components v sub I of q times v bar sub j of q bar, then these components v sub I of q can be regarded as components of a vector value modular form, which we can take to be of dimension d. So this is a d vector, and so is this. And there's some representation rho under which the entire vector transforms under SL2Z. Near the cusp at infinity, we take each of these components to have some Fourier series where the leading power is m0 of I, and then there are some subleading powers where m0 of I in general can be real, and we are going to take the Fourier series to have this form where the subsequent powers are off by some rational powers, rational numbers. And so these coefficients here are otherwise unconstrained so far, except we're going to take them to be constants because we're imposing that this is a discrete function. There exist things called logarithmic VVMFs, where, for example, this has some powers of tau2, then you can think of it as logarithms of q, and these are called log VVMFs. But unless you're studying log CFT, these aren't terribly relevant. Now, one useful way to think about VVMFs is that their components solve modular linear differential equations. So the component I is a solution to an equation of this form, where this differential operator is defined as the composition of these modular covariant differential operators. Okay, so we just take q dq minus some constant times the modular connection E2, and we just shift the weight of these guys according to this index here, and we compose them like so. And you can take this linear combination of such differential operators, and then the statement is that the components of the VVMF solve an equation of this form. These functions f are themselves, in general, meromorphic modular forms of weight 2r, and poles, and with poles of order less than or equal to L. For this talk, I'll take L to be 0. So these are actually holomorphic, so E2, I mean E4, E6, etc. And we're going to take the dimension d to be greater than 1 just to avoid trivialities about constants and so on. This is sometimes known as the monic case, because when L equals 0, you can put the equation in a form such that the leading term has coefficient 1 and otherwise no q dependence, where these are holomorphic. Now, an important fact, about this equation is that there's an additional equation for solutions, which implies the following universal property of VVMFs. The sum of all the leading coefficients of each component equals something which is just d dependent, d minus 1 over 12. And this is fairly straightforward to see. Now, we're going to be interested in the quantity m naught, which we define as the minimum of all of the leading exponents. So m naught of I, remember, is the leading exponent of the ith component of a d-dimensional VVMF. Since the right-hand side is positive, this thing can have either sign a priori, and indeed, in general, it can. So for some familiarity, let's just take d equals 2. This is the most general form of the equation that I just wrote. And solutions are actually known in some elegant closed form in terms of 2f1s. Okay, so mu is some parameter relating to gamma, and j is the modular j function. The general form is not terribly important, but it's a nice formula, so I put it up here. For example, if we take mu to have whatever value we need to have to get these exponents here, then this is the expression for these two components. So in this case, m naught is 1 over 84. That's the smaller of these two exponents. On the other hand, clearly the coefficients don't seem to obey integrality. And indeed, with a little bit more effort, one can see that no matter how high you go in the Fourier expansion, the denominators are always growing unboundedly. So there's no integer by which you can multiply both components and have the Fourier coefficients be integers. Now, there's a mathematical conjecture about the implications of integrality for VVMFs. The conjecture is the following. If you assume that the leading exponents are rational numbers, then if there exists an integer m such that all entries of m times the VVMF have integral Fourier coefficients, then all of the components of the VVMF are actually themselves independently modular functions for a principal congruent subgroup gamma n of SL2Z for some integer n. So gamma n is defined as the subgroup of SL2Z matrices, which are equal to the identity modulo n. Now, this conjecture has been proven for d equals 2 and 3, and it is widely held to be true in general in the math community. There's a lot of works by these authors proving and looking at examples of various types. It's sometimes known as the unbounded denominator conjecture, which is just the contrapositive of the statement that I'm making here. So they often look at forms which are not such modular functions and show that the resulting Fourier coefficients have unbounded denominator in the Q expansion. Originally, this was stated for scalar modular forms, but then extended to vector valued modular forms in the way that I'm describing here. And there are other sort of versions of it that have been thought about. So we're going to prove the following theorem, which is predicated upon the integrality conjecture, and which will give us some nice physics data. So the theorem is the following, the one I stated earlier. If we have some SL2Z invariant function f, which is weakly holomorphic, and admits a decomposition into VVMFs, if we write the Fourier expansion like this, then integrality of these coefficients implies that the leading exponents are negative. So this is something that we prove rigorously, but we use physics ideas, and it's simple enough that I'm going to walk through it. It's a two-step process. First, we're going to prove an intermediate theorem about modular functions for this congruent subgroup, and then we're going to apply the integrality conjecture. So before I do that, are there any questions about this modular stuff that I've introduced so far? Okay, so step one, we're going to prove some theorem about modular functions for gamma n. I think it's worth doing, and hopefully it won't take too long, and it involves a picture, so bear with me. So the theorem is the following. If we have a d-dimensional VVMF, and we define m naught in the way we did before, if there's at least one component, which is a modular function for gamma n for some n, and the leading exponent for that component is non-zero, then m naught for this vector valued modular form is negative. So what is the proof? The proof relies on something known as the valence formula for modular functions of gamma n. It's a statement that if you take the sum of order of vanishing at all poles and zeros in the fundamental domain for gamma n, that this sum for weight 0 functions equals 0. So if this function vi has a pole somewhere in the fundamental domain for gamma n, then you get a negative contribution times where the number is just minus the order of the pole. And if there's a 0, you get a positive contribution. Here I've just labeled the location in the fundamental domain P, just because. So this is a fact about modular functions of gamma n. So now let's assume we have some component by construction which has a leading exponent which is positive. If it's negative, then the proof is trivial, right? M naught is the minimum of all of them, so obviously M naught would be negative. So we're going to assume there's some component where the leading exponent is positive. Now, since, as a result, that component vanishes at the cusp at infinity, it must diverge at a different cusp in order to satisfy this equation. Now we can form the SL2Z invariant where we sum over the squares of all components. And therefore, some component of V has a pole at infinity because I can do an SL2Z transformation to map the 0 at the cusp for this guy to a pole somewhere else for that guy. And likewise, that means there's a pole at infinity for a different component. And that's the proof. So here's a picture. Here's, for example, the fundamental domain for gamma 2. If we have a component that has a 0 here, say at the cusp at I infinity, then it has to have a pole at one of the other cusps, say here or here. But now if we form the SL2Z invariant, that implies that there's a different component which has a pole here, which reproduces the pole that the other component has here. And that same component, by the way, would have zeros here. But all that matters for us is that we've established that there's some component which has a pole at I infinity, and that was the idea. So the proof, I think, is pretty intuitive. And now we can combine it with the integrality conjecture to prove the desired statement. So first, we're going to assume that leading components have rational exponents, because that's where the integrality conjecture holds. Then we apply the conjecture, and then we apply the previous theorem, and that's it. And here it's important to note that the initial equation implies that at least one component has to have positive leading exponent, because the sum of all the components was a positive number. Okay. Good. So to summarize, if we have a vector value modular form that is discrete and integral, it diverges at the cusp. At least one component has a negative leading exponent. So this is a mathematical result, and we're going to extract some physics from it. And the physics follows from viewing this form, this function f, as a rational CFT observable on the torus. And there are different observables we can choose, and we're going to get different results. So the first one is quick and less interesting. Let's take f to be a partition function. So the leading behavior near the cusp of a partition function is q and q bar to minus c effective over 24, where c effective is defined in this way. This is just a definition. So the statement that m naught is negative implies that actually all rational CFTs have positive effective central charge. Note that this is only a non-trivial statement about non-minimal Virasoro CFTs with c less than 1. Right? If c is greater than 1, then c effective equals c. And now if c is less than 1, then it is known for the minimal models that c effective is non-negative. But there are non-minimal Virasoro CFTs, in other words, those with c less than 1 that don't lie in the minimal series. And so this is just a statement about that perhaps odd set of CFTs, which nevertheless some people have sometimes thought about, and I'm not aware of a proof of the effective central charge being positive for those. More interesting.
Eric, yeah, about this result, does the usual Carty argument tell you C effective have to be positive? Because C effective will be what appear in the square root of the Carty formula.
Yeah, I think it doesn't tell you the C effective has to be positive. I think it's the other way around, that I don't see, you know, unless you have an independent argument that it has to be exponential and real at large dimension, then you don't get to conclude that. And I'm not, maybe such an argument exists, but you know, these are quite odd theories, so I don't know whether it really does exist.
Okay. Okay. Thanks.
Yeah. Let's instead take f to be the difference of partition functions of two CFTs with the same central charge. Right, so we can do this because we're not insisting on positivity. Let me just remind. So if the CFTs have identical spectra of twists up to C over 12, then when we take the difference of their partition functions, f must in fact be trivial, otherwise m naught, the leading exponent, would be non-negative. But we just proved that that's not allowed, at least for functions constructed out of vector-valued modular forms. In other words, rational CFTs obey twist determinacy. So as a picture, if I have a CFT1 with this spectrum, and CFT2 has the same spectrum up to C over 12, then in fact the spectrum above is the same as well. In other words, the twist spectrum with T greater than or equal to C over 12 is uniquely determined by its complement. This result, I think, is really interesting and surprising, and it mimics the same statement about holomorphic CFT, where it just follows from known facts about modular forms. Here, it's far from clear that this had to be the case, and I don't think this was believed to be the case. Rational CFTs are nice in many ways, but being non-holomorphic, there is much less known, and I was surprised by this result. There's a corollary, which is that there's at most one rational CFT partition function with a given extended chiral algebra and central charge C, where the twist gap is greater than or equal to C over 12. Right? If there were more than one, then you take the difference and you would get a non-trivial function f, but you can't. Okay. In other words, such theories would have to have just the vacuum below C over 12, but there can only be one. So can we go away from saying things about the spectrum and talk about the OPE? And remarkably, we actually can. So now let's take f to be a torus one-point function of some operator O times some eta functions to make this thing modular invariant rather than modular covariant. A torus one-point function of a local primary O admits a conformal block decomposition. So in an OPE, there are OPE coefficients which appear linearly, this being a one-point function, times some blocks f, where f is taken to have a Q expansion starting with this power. So in a rational CFT, the rescaled blocks, rescaled by eta functions, are components of a vector-valued modular form, just like the partition function is a sum over products of components. So now we can ask a bootstrap type question. Given some operator O, which appears in the OPE of some operator phi with its conjugate phi dagger, what is the upper bound on the twist gap to the lowest twist operator phi star? So in other words, what is the upper bound on the leading power of Q in an expansion like this? To use the previous results, we have to know when conformal blocks are integral. Now, in general, they're not. In minimal models, there are many examples where they are, and in the appendices of our paper, we check the statements that we make against those examples, and it works very nicely. But what we're after here is a more general classification that goes beyond minimal models. And so we need to know when conformal blocks happen to have integral Fourier coefficients. And I just want to emphasize it's a statement about the blocks. The OPE coefficients can be irrational, they can be whatever you like. The components of the VVMF are the blocks times eta functions. Now, there's a striking fact about torus one-point blocks, which is that when h equals 1, the block is actually just a conformal character for the module of phi, the internal operator. This follows from conformal invariance. So take your dimension 1 operator, integrated over the circle, it has weight 0. That's one way to think about it. And this is a known fact. We're not the first to derive this. But it's therefore got integral Fourier coefficients. And aside from the case h equals 0 and h equals 1, I believe that there are no other such cases where the Fourier coefficients are integral, but that's not a proven statement. It would be nice to prove that. Anyway, so a particularly interesting subcase is when O is a marginal scalar, when h and h bar both equal 1. And indeed, if O is exactly marginal, then the OPE coefficient of O with O and O dagger is 0. by virtue of the vanishing of the one loop beta function. And likewise for an operator which is marginal to one loop. But I'll just phrase things in terms of exactly marginal operators here because the conclusions are especially interesting. So putting all these things together, we learn that any rational CFT with an exactly marginal operator O with a non-zero one-point function must have some primary phi star, which is not O due to this condition, satisfying this bound on its twist and having a non-zero OP coefficient with O. Moreover, the contributions to the one-point function with twists less than this bound uniquely determine those with twists above this bound. This +2 comes from the eta functions required to define this weight 0 object, and the 2 is 2 times 1, where 1 is the weight of the operator we're talking about. So that's the same result. Let me just make a few comments. I want to emphasize that because we're using torus one-point functions to make statements to derive bootstrap bounds, phi star is necessarily non-holomorphic. If O is a primary under the extended chiral algebra, then it does not live in the chiral algebra, and therefore the vacuum module does not contribute. So that gets rid of a lot of contributions which otherwise might spoil statements about the more interesting part of the spectrum, which is the spectrum of primaries. Compared to the 4-point function bootstrap, this is a really nice thing, where you have to always worry about the vacuum, and indeed the existence of the vacuum is what makes a lot of the modular bootstrap stuff hard. Here there is no vacuum contribution. The second comment is that we're using integrality of the conformal blocks, but what we're actually getting is a result about determinacy of the OP coefficients above this threshold. And finally, on the matter of interpretation, since we're talking about exactly marginal operators, this OP coefficient is related to the first order anomalous dimension of this operator phi. I'm going to reserve comment about that until later when we achieve a similar bound on delta star. But before moving on, let me just pause for questions. Okay. So quick comments that probably isn't time for. Yeah, I guess that's about right. So there's some things we did, some things we didn't do. Let me just highlight the last comment, which is the statement of twist determinacy of something we prove for rational CFT. Whether it's true for irrational CFT is still an open question. We did not address that. I think it would obviously be interesting to do it. Okay, so now we're going to move on to the dimension spectrum part of the talk, and then some 3D gravity discussion. So forget about vector value modular forms, forget about rational CFT. We're going to return to the general setting of non-holomorphic irrational stuff and see what we can say. So now let's consider modular functions restricted to the imaginary axis. So we're going to take q bar equal to q and ask what we can say about the q expansion. So here x naught is defined as the leading exponent. It's the minimum of the sum of leading exponents in q and q bar, which are glued together by the gluing matrix n, whatever that might be. Because of the fact that this gluing matrix enters into this construction and the gluing matrix is not in general determined, this introduces more difficulty and requisite knowledge of the space of admissible gluing matrices if you want to say anything completely general. But still we'll be able to make some progress. And the theorem we're going to prove has two parts and can just be stated very simply. The theorem is the following. There do not exist non-holomorphic cusp forms satisfying positivity, discreteness, and integrality. On the other hand, there do exist such forms if you drop positivity. So let's prove this. The proof is quick and may even be known to some modular people, but here it is. So first, let's recall that discreteness means that these are constants, these coefficients a sub x. we insist that it's a cuspidal form, and that means that as q goes to 0, this must vanish. So in other words, x naught is positive. Now, under S invariance, the cusp at infinity gets mapped to 0, and so q indeed goes to 1 in that S transformed frame. And so f1 comma 1 equals 0 by S invariance. But if you just plug in q equals 1 here, you just get a sum over the degeneracies restricted to the imaginary axis. So you have to satisfy this equation, and you can't do that if the a's are all positive, much less integral. That's the end of the proof. A corollary of this is if we allow negativity, then integrality plays a key role too. Integrality would imply that you have to have an infinite number of negative coefficients in order to satisfy this equation. So this proof is nice because it's very clear where discreteness and integrality are both playing a role. Discreteness is crucial because if instead you have some a's which depend on tau2, then in the step where you take tau2 to 0, you can get a vanishing of the sum even if the coefficients themselves don't vanish, right, or don't have to sum up to 0. So discreteness and integrality are really important for this proof, and that suggests that those are important properties for constraining the space of non-holomorphic modular forms. I should say I presented it for modular functions, but you can take this to have arbitrary modular weight. All that will happen is that when you go from this frame to the S transformed frame, you get some powers of tau2, but because the vanishing is exponential, those powers don't matter. Was there a question? Sorry. No? Okay. So we have to relax positivity if we want to find non-holomorphic cusp forms. Okay, fine. Can we find discrete non-holomorphic cusp forms? So first we looked around and we didn't find any. There are 3 main classes of forms in the literature. All of them are continuous, that is to say they have Fourier coefficients which depend on tau2. So the first class are so-called Moss forms, which are defined by a Laplace equation on the upper half plane. The canonical example of a Moss form is a non-holomorphic Eisenstein series. These have appeared in many settings recently and are well studied by mathematicians. It's easy to see that these have powers of tau2, infinite powers indeed, in the Q expansion. The second class is newer. It was constructed by Francis Brown in a series of papers from 2017, which I think were sort of garnered some attention in the math and physics worlds for some new inroads into the world of non-holomorphic modular forms. He built some new families of cusp forms out of holomorphic cusp forms. So given some holomorphic cusp form, he have some algorithm to turn it into a non-holomorphic one. But you can check explicitly that the forms he articulates in his paper, anyway, are continuous. And finally, there was a nice paper by Justin and Eric Doker, where they constructed some new families of cusp forms by thinking about modular graph forms, which are these objects appearing in string perturbation theory. And those forms also all are continuous. Okay, so we're gonna have to invent some, but it's actually easy to do this. And it's easy to do this using physics. So what I mean is that to make a non-holomorphic cusp form, all you have to do is take some known CFT partition functions and take linear combinations and products such that the result is cuspidal. So in other words, in physics terms, you take linear combinations such that you cancel all the states below C/12. So a simple example, and we give many examples in our paper of different types involving WCW models, other rational models. A nice example here is just taking the difference of a compact boson of radius r, take the difference of its partition function with the orbifolded partition function. And you can check that in the Q expansion, the leading power is this, where I'm using a convention where r squared is greater than or equal to 2. And so for some range of r squared, this is cuspidal, right? Good, so that actually turns out to not be so hard, and it gives a kind of toolkit for modifying the non-polar degeneracies of a non-holomorphic CFT partition function. Now you might ask, how cuspidal can a non-holomorphic cuspidal function be? We don't know the general answer to that question, but for those which are constructed from gluing vector-valued modular forms, a very simple argument from the initial equation implies that x naught, the leading exponent, is bounded above by d minus 1 over 6, where d is the dimension of the vector-valued modular form. And we'll use that in a second. I should stress that this bound is surely suboptimal, because we're assuming that there exist gluing matrices which make modular invariant functions out of these vector-valued modular forms, such that this can be realized. I suspect that's not possible, but the classification of all modular invariants constructed out of VVMFs is not available. And more generally, there's no general bound. That is to say, there's no upper bound that could exist. Now, you can just take powers of VVMFs, and that drives x naught arbitrarily high if the VVMF has an x naught which is positive. But it drives down m naught, right? So if m naught is negative and x naught is positive, and you take a bunch of powers, then you're driving down m naught at the cost of increasing x naught. And if m naught is supposed to not go lower than, say, minus c over 24, then in general, there is a bound, but that comes from physics, not from math. So this is still an open question. Okay, that was meant to be an aside. So we have some math. Let's get some physics out of it. Let me pause for questions before we do that. Okay. So let's take f to again be the difference of partition functions. We showed that there exist non-holomorphic cuspidal functions. Therefore, at least on the basis of modularity alone, the spectrum with dimensions greater than c over 12 is not determined by its complement in a compact unitary irrational CFT. In other words, discreteness and integrality and cuspidality are consistent with each other, and we explicitly constructed these forms, so we know they exist. However, as I mentioned before, such forms have an infinite set of negative degeneracies. And the claim I want to make is that a typical irrational CFT cannot support these while preserving unitarity. So the claim is that absent fine-tuning in the space of cuspidal functions and in the space of primary partition functions of CFTs, the primary spectrum with dimension greater than c minus 1 over 12 is actually determined by its complement. Now let me elaborate on this a little bit. First, just a technical remark, c minus 1 appears here because actually if you run the same kind of argument using the primary partition function, which has weight, then you get, you win a little bit by using forms instead of functions. That's not terribly important, but that explains where that's coming from. So just to say this another way, if you can add functions to your partition function which have an infinite set of negative degeneracies, and you want the resulting function to still represent the primary partition function of a unitary CFT, then these obviously have to line up very precisely so that you don't have any non-unitarity anywhere. And to quantify this rigorously, you would need both an accounting of the space of partition functions of irrational CFTs, an accounting of the space of cuspidal non-holomorphic modular forms, and a measure on these spaces from which to draw. None of these is available. And so the perspective that we're taking is that if we take a typical CFT, or perhaps a typical cuspidal form, then there's no such match in these two spaces which preserves unitarity. This is just another kind of way to invoke usual notions of chaos in irrational CFT, which relies on the spectrum. So here I'm making a statement that a typical chaotic CFT may have a very dense spectrum, but the actual dimensions are sporadic, and the dimensions delta are irrational. And so the probability of finding a cuspidal function which has negative degeneracies, an infinite number of them, all of which have sufficient support on that CFT partition function, is small. So the claim goes beyond just math, but I think it's well supported by familiar notions of irrationality and chaos in physics. And of course, it would be nice to make that more concrete, difficult as that may seem. So the second consequence, and then we'll move on to the 3D gravity part of the second consequence of our mathematical result is, again, if we take f to be a torus one-point function, then by the same logic as before, let us restrict to the rational CFT realm. Okay, then we get to conclude that any rational CFT with an exactly marginal operator, with a non-zero one-point function, has to contain another primary phi star, which is not itself O, which satisfies a bounded dimension. Now there's this parameter epsilon. If O is diagonal, then epsilon is 0 because the leading exponents on the left and right are the same, and the dimension is just twice the minimal twist. If O is not diagonal, then we had this bound before on the maximum cuspidality of an object formed by gluing vector value modular forms. That was this d-1/6. And so that's what this number is, where dO is the dimension of the vector value modular form appearing here. In operatorial language, that's just the number of operators phi in whose OPE O appears. And likewise from before, the contributions with dimensions below this threshold uniquely determine the contributions with dimensions above the threshold. So now we're back in the rational realm, but this is a very interesting statement. It's a constraint on rational points of conformal manifolds. Again, phi star is necessarily non-holomorphic if we assume that O is primary. We've checked this in some familiar rational models. One limitation I should highlight is that it does not apply to current deformations. So if O is a JJ bar deformation, which is exactly marginal, it does not apply because O is neither primary with respect to the extended chiral algebra, nor does it have a non-zero one-point function. So there's a lot of familiar examples where that's the case. This doesn't apply to them, but you can't win them all. Now, as promised, let me elaborate on the consequences of this, this fact that O is exactly marginal, right? Because of the fact that an exactly marginal deformation implies that the first order anomalous dimension is proportional to the OPE coefficient phi dagger O, this primary phi star can be thought of as the lightest primary which acquires a non-zero first order anomalous dimension in conformal perturbation theory. In the superconformal setting, this operator is necessarily non-BPS, so you can think of this as a constraint on the existence of non-BPS operators. Another interesting thing about this is that this DO, because of this translation, is the rank of the one-loop dilatation matrix, right? Whereas in OPE language, DO is the number of operators phi in whose OPE O appears, but thinking of phi as the number of operators which acquire anomalous dimensions, then that's what DO is. It's the number of such operators. And so the bound relates DO to the tree level dimension of the lightest operator phi star. So in general, this seems to indicate that there's some hidden degeneracy in the one loop dilatation matrix as one perturbs away from free or rational fixed point along a conformal manifold, and I think that'd be really interesting to try to codify a bit further. So, good. Final comment before we move on to 3D gravity. So at large C, an obvious thing about this, maybe the first thing a lot of you noticed, is that the bound coincides with the classical threshold for BTZ black holes in theories of Idiot's 3 gravity. That is to say, at large C, this goes to C over 12. Where I'm imagining holding D constant. Now, in order for that result to hold, we had to take the CFT to be rational. So taking large C while preserving rationality and finiteness of the dimension D can only be done if you enlarge the chiral algebra. In general, for a rational theory, the central charge is bounded below by, let's call it C currents, which is the asymptotic central charge of the vacuum module. So the holographic interpretation of the bound is that of a massless scalar, dual to the exactly marginal operator, coupled not to Einstein gravity, but to a higher spin gravity with an infinite number of gauge fields. On the other hand, it should be emphasized that the bound constrains the non-holomorphic spectrum CFTs which are, of course, irrational with respect to Virasoro. So in that sense, this is kind of halfway to the sought-after modular bootstrap bound for generic irrational Virasoro CFTs, where it's believed that every such CFT has to have, besides the vacuum, a primary with dimension bounded above by this. We have not shown that, but we've shown that for rational CFTs with exactly marginal operators, that is true. Okay, so as I segue to 3D gravity, let me ask if there are any questions about this non-holomorphic CFT segment.
So here you're getting this bound from assuming that there exists exactly marginal operator. Is that right?
Mm-hmm. Yeah.
What if it doesn't?
If it doesn't, then we don't have any bootstrap bound to derive, because when we take our function f to be a torus one-point function, the power of our results relies on integrality of the Fourier expansion of the components, and so we have to ask when conformal blocks have that property, and they only do when the internal operator dimension on the left is 0 or 1. 0 is the identity, 1 is exactly a marginal case.
So in the case of pure gravity, I mean, there's no marginal operator, right?
That's right, but you can ask a very slightly different question, which I think is interesting in and of itself. Let's not ask about the purest of the pure theories. Let's say we have a CFT with a normalizable vacuum and an exactly marginal operator. So if you're interested in theories with conformal manifolds, what are the bootstrap bounds on the rest of the spectrum? So that's the kind of question that we're answering here, at least for this class of theories.
All right, thank you.
Yeah. So in the bulk, you're just adding one field. You think of it that way, and then you can ask what else has to be there. Any other questions?
Can I ask a question?
Of course.
By turning on this exactly marginal operators, or I mean the central charge remains to be the same. This is not very naive question. Can you explain about that?
Well, the central charge is constrained to be the same by the C theorem. So everywhere along a fixed line or conformal manifold, C is the same. And so because of that, the bound is uniform. I mean, but of course, this bound applies at the rational point, but the statement you made is a statement that follows from the C theorem.
I see. Okay, thanks.
Sure. Any other questions? Okay. So just a few comments about 3D gravity, and then I will conclude a little bit over time, but all right. So this part is less rigorous, but we're just trying to unpack some of the implications of our results in the ADS3 CFT2 context. Let us write the partition function of a putative theory of pure 3D gravity in ADS3 in the following way. We have the vacuum state, which corresponds to say, global ADS in the bulk. And we're going to write the rest of the spectrum as an integral of some density of states rho of H and H bar times conformal characters. At leading order in large C, the lower bound for these integrals is C over 24. There are, in general, going to be corrections to that. We'll talk about that in a second. And here I'm not committing to whether the bulk is dual to an ensemble average or a single instance of a CFT. That is to say, whether rho is continuous or discrete. And so in both cases, there will be some kind of implication of our results for the interpretation. So let me talk about each of these in turn, and then I'll conclude. So this is just in the spirit of making some comment on this burgeoning subfield. So suppose the dual is an ensemble average of CFTs. A continuous spectrum with a gap above a normalizable vacuum is a feature of ensemble average systems. So if we want to view pure 3D gravity as dual to such an average, then the possible existence of continuous positive cuspidal functions would suggest that there's not a unique ensemble average dual to pure 3D gravity. So let me say that another way. We showed that discrete positive integral cuspidal functions do not exist, but the proof showed that if the function is continuous, then that is not necessarily inconsistent with positivity. So there may exist continuous positive cuspidal functions. And if there were, then you can add them to a function like this, and you would be tweaking the density of states. In other words, a partition function of this form would not be unique. This, I think, is sensible in the following sense. If you're trying to do an ensemble average over the space of CFTs to get something like this, and of course no one knows how to do this quite, then there may be ambiguities in that procedure, and the cuspidal functions parameterize these ambiguities. So people are wondering which subspace of CFTs should I average over? How do I average? With what measure do I average? And I'm not sure there needs to be a unique answer to that question. And you might view the existence of continuous positive cuspidal functions as telling you that there is not a unique answer, because you can always add such a function to this while preserving all of its features.
Eric, can I ask? Because why do you say that continuous spectrum is a feature of ensemble average system?
Well, so first, well, I guess there's a few ways to answer this. So the first is by way of reference to the JT gravity 2D story, where it's been observed that simple semi-classical calculations of 3D gravity give continuous densities of states, which can be reproduced by ensemble averages in 1D. In ADS3CFT2, the original calculation of Maloney-Witten, where they attempted to compute the 3D gravity partition function under a certain restrictive set of assumptions, produced something continuous, as do all Poincare sums over conformal characters. And so any kind of fairy tale-like calculation of a pure 3D gravity partition function or something like it will give you something that's continuous. And we know that compact CFTs do not have spectra like that, but in certain settings in 2D now, thanks to the work of Maloney-Witten and Afkhami-Judi et al., it's been shown that ensemble averaging over the Narain CFTs gives you something which is a continuous density of states. So to summarize, we know that a compact single CFT does not have a continuous density of states. And there are explicit calculations showing that ensemble averages in a controlled way do give you continuous densities of states.
Okay.
I have a question regarding to that answer.
Yeah.
So in JT and the 1D quantum mechanism, the discreteness that you said is continuous spectrum, isn't because of large n limit? Like in quantum mechanics, you probably have a discrete, but taking large n, it looks like a continuous, like a matrix model in the long time ago.
Yeah, I think, right. I guess I feel like the verdict is still out on what so in ADS3, if we're trying to, so I'd say currently the questions that seem most interesting are the ones that pertain to what happens in the semi-classical limit of a sequence of theories. And so there we know that there's this continuous spectrum that emerges. So whatever happens in the finite C realm, what we want to know is how to get something which has that property at large C. And so there, that's the nature of the calculations I was referring to. But I guess I don't feel like I have anything firm to say about what's supposed to happen in the dual to quantum pure 3D gravity. I mean, that actually could mean any number of things. I'd be curious to hear other people's opinions, but I guess I would say that even the semi-classical questions are the ones that where the connection to ensemble averages seemed firmest. And I guess that's the nature of your comment, so I think I agree.
And I have one more question. It might be a very stupid question, but when you do the ensemble averaging, you just average over the partition function. But sometime in the condensed matter, people also average the free energy, like quenched averaging and annealed averaging. But in this partition function of the gravity, it might be very different between the annealed. What I mean is average of the partition function or average of the log of z or free energy. So would it be very different result? Give a very different result from this in this gravity point of view in 3D?
I think from the gravity point of view, the answer is no, just because, you know, at leading order in the classical limit or even in the semi-classical expansion, the two are related very, very directly, you know, just in the kind of naive exponential way. So you know, the answer you're trying to understand or reproduce from the bulk does not have any distinction between those two. So whatever the procedure is in the CFT side should reproduce that. But yeah, I think again, maybe for more ambitious questions, that distinction might appear.
Okay, thank you.
Thanks. Any other questions? Okay, so now let's suppose the dual is a single instance of a CFT. So here's our gravity partition function, and we're going to take rho to be discrete, so a sum of delta functions. So now there's an interesting connection between the uniqueness of pure 3D gravity and the location of the black hole threshold. So let us include quantum corrections to this threshold and say that the lightest state above the vacuum has dimension c-1/12 plus some little delta star. So if this delta star is positive, then modulo fine-tuning of the sort I described earlier, z is unique. Z is unique in that situation because if this is positive, right, then to modify the partition function, you have to add a discrete integral cuspidal function. And unless you want to avoid fine-tuning, aka an infinite set of negative degeneracies, which you have to have perfect support on, this does not exist. On the other hand, if delta star is negative, then you can change this partition function without having to add a cuspidal function. You can just add something which has some divergence at infinity, and we know that there are lots of these functions out there. And the proof that I gave of their non-existence does not apply unless you impose cuspidality. Right? These would just be like, for example, a partition function of you know, some low central charge CFT. The leading term goes like q to the minus c/12. So where is the black hole threshold gets mapped into a question of uniqueness of pure 3D gravity if you take it to have a discrete spectrum. So a naive guess for what this threshold value is 0. That follows from a few different places. At asymptotically large dimension, the Carney formula has a c-1 shift if you look at the primary density. More refined calculations in a paper by Nathan Benjamin in the audience and collaborators, which I guess included me, looked at small black holes near the threshold and tried to compute their entropy more rigorously using holomorphic CFT techniques. And you can also observe this c-1 in that setting. But there's never been a good argument for or proper calculation for where the black hole threshold is in pure 3D gravity. And so here's one idea for where we might look. At large spin, so away from the absolute threshold of the dimension, if you look at states as a function of spin, then the lightest non-vacuum state of spin j has this dimension, where delta star j was determined in a paper by Maxfield and Toriachi at asymptotically large spin and large central charge. So what we're asking is, over all values of spin, what is the lightest state? In other words, what is the minimum of this linear combination, and is it positive? And one idea to determine that is to try to use some version of conformal Regge theory adapted to the Virasoro setting in 2D, which has never been done, to continue this result of Maxfield and Teriachi down to finite spin. And if you had some analytic trajectory in spin, say, then you could ask whether the lightest state on that trajectory is above or below C minus 1 over 12. So that's an idea for the future, but I think this connection between these two questions is nice and fun to think about. So let me summarize. This was a slide from before. I think we talked about all of these topics at this point. As for whether the irrational CFTs really are as wild as we think they are, I think in some ways, no. Certainly rational CFTs are less so. And so there are many different future directions in each of these three prongs. Just to highlight a few, in the world of discreteness and integrality in the space of CFTs, I think it would be very exciting to try to combine this with traditional bootstrap methods rather than thinking of this as a kind of alternative where we don't use positivity. I don't have great things to say about how to do that, but if we could use the modular bootstrap combined with discreteness and integrality as an input, that would be fantastic. As far as non-holomorphic modular forms go, it's still highly unclassified, but we showed that imposing discreteness and integrality really cut down on the possibilities. So I'd like to see what more you can do. And in the world of 3D gravity, we talked about this last one, but I think it might be nice to actually see if we can construct positive cuspidal functions, not just to know that they may exist, but to find some that do exist, and to try to use them to understand how to ensemble average in 3D gravity and what they might imply about 3D gravity itself. So I'll stop there. Thanks.
Thanks, David, for the wonderful talks. And time for questions or comments.
Can I ask one question?
Sure.
So yeah, first, thanks for a very nice talk. So that, so in the beginning you mentioned that all the well-controlled examples of holography involves exactly marginal operators, right? So can you somehow get that fact from your argument, saying that if you start from the holographic CFT, then that implies the existence of like exactly marginal operator, or at least suggests something like that?
Well, actually, I don't think I said that, but I don't necessarily disagree with it. I guess I was trying to be sort of agnostic about whether good examples of holographic CFTs should have exactly marginal operators, but certainly in string theory these appear. So this is, I agree, it's well motivated. Yeah, I think I feel that we'd have to get away from the rational point on the conformal manifold to really say anything of the sort you're talking about. So there are lots of examples where there are rational points in the conformal manifold, but if we want to say something about what happens away from that point and to what extent that the spectrum of that theory is organized in a certain way in the holographic regime, yeah, that would be great. But I think as long as we have to use vector valued modular forms, then we're stuck in rational CFT land. So yeah, I think it's a really important question for us physicists to think about the world of non-holomorphic modular forms and see if we can, make some real progress there. But I think without that, maybe it'll be tough.
Thanks.
More comments? Questions?
I got a question about this continuum spectral limit, which is related to the holography. So, well, you have already explained, I guess. So this semi-classical largest limit could be enough for explaining this continuum continuous spectra, or do we need this ensemble average? Can you clarify a little bit further? Do we
Sure.
need?
So Let's see. So I would say, first of all, I think it's still an open question about whether ADS3 gravity is dual to an ensemble average or not. And it's also, I mean, it's a very open question in the sense that what it means to ensemble average to get something which would be dual to pure 3D gravity has not been defined or understood. I mean, one thing people say is that what are you averaging over? If pure 3D gravity is supposed to have no moduli, no states up to the black hole threshold, then there's no couplings to average over, so what are you averaging over? There may be some abstract way to do this in the space of solutions to the Bootstrap equations or something, but that's not been understood. So it's very much an open question about whether the duality involves an ensemble average in 3D gravity if you insist on a very sparse spectrum of the type that pure 3D gravity would have. I guess I also feel like it's an open question whether there's a unique answer, as I tried to explain. But I think I don't really have a good intuition for the answer to the same type of questions if you ask at finite C, because, I mean, the question we're trying to answer is motivated by what 3D gravity looks like. And what 3D gravity looks like is something that we understand in the semi-classical limit much better. So, you know, we're kind of trying to match the properties of ADS3 gravity in the semi-classical limit, but if you handed me a quantum theory, then maybe the spectrum doesn't look continuous, or maybe it has features that we wouldn't expect of ensemble averaging, and then maybe we just wouldn't think to look at that. So I hope that answers your question a bit, but maybe the spirit of my answer, if I could summarize it very briefly, would just be that I think it's sort of wide open as to what the dual is supposed to look like. And, you know, there's been a lot of excitement about ensemble averages, but we still have a lot to understand about what that even means.
Okay, thanks.
I'd invite other people's perspectives. I mean, it's a fun topic to discuss. I guess we discussed it a bit yesterday with Christian, but
Thanks.
Can I ask you for clarification? So you mean that this like continuous spectrum appears only at large C, or can it be a feature of finite C?
I mean, it could be a feature at finite C. For example, I mean, in this Narain story, there's an average they do, and they get an answer which depends on C and is continuous for whatever value of C you pick. So there are some non-holomorphic Eisenstein series which appear after you do the average over the set of CFTs, and the index of the Eisenstein series depends on C. But for any index, it's a continuous function.
Yeah, I mean, like, the reason why I'm bringing this up is that, like, if it's a behavior at large C, then there are some examples where things can look like continuous spectrum, like where the gap goes like 1 over C. Yeah,
I think I think that's not the kind of thing that people are seeking, but maybe it's just not. Maybe we need to think more carefully about what exactly, excuse me, the distinction would look like. Maybe people have, and I just don't. I'm not representing it well. But yeah, I think the kind of thing where we say that at infinite C, the spectrum is effectively continuous because the spacings are e to the minus s, and s is going to infinity. I think it's something different that is being sought.
All right.
More questions? Comments? All right, if not, let's thank the speaker again. Thank you, Eric.
Thank you. This was fun. I appreciate the invitation. Thank you again.
Thank you.
Thank you.
All right.
So this is the end of the morning session.
Okay, so let's meet this afternoon again. Okay, bye.
Bye.